All right, so let's begin section 4.3. This section introduces prime numbers, gives a few results about prime numbers, and then discusses a little bit the importance of prime numbers. So let me say a couple things about primes before we get started. First thing is that any study of integers is going to need to discuss primes, because as we'll find out soon, integers are made up of prime numbers. They're like the building blocks of integers. And so the relationships between integers all have to do with their prime, what's called the prime decomposition of those numbers. So we'll look into that. And the other reason that we care about prime numbers is for the group that's going to give do a project on cryptography. Cryptography is built around the idea of using very, very large prime numbers to make encryptions difficult to break. If you use very large prime numbers, it can be and sort of like obscure what prime number you're using, then it can be very difficult to figure out how to break an encryption. And by difficult, I mean like the algorithm that would break it is would take an unfeasible long amount of time. So that's kind of the whole crux of encryption. But I'll let that team discuss that in greater detail, of course. So let's begin this lesson with just an observation. First of all, if you take any positive integer n, all right, so not 0, but any positive integer, it's going to be divisible by 1, because 1 divides any integer, and also itself, n, right? Every number divides itself. So for n equals 1, that means there would be exactly one divisor, 1 itself, right? But for any number larger than 1, there's going to be at least two divisors, 1 and n. There may be others, but there's going to be at least two. So the definition of a prime number is an integer, we'll call it p for prime, which is greater than 1, whose only divisors are 1 and p. So like I said, every number that's bigger than 1 is going to have the 1 and itself as divisors, and a prime number is a number whose only divisors are 1 and p. There are no others. So a few examples of prime numbers would be like 2, that's the smallest prime number. And it's the only even prime number, because every other even number is divisible by 2. And then like 3 and 5 and 7 and 11 and 13 and 17 and 19. So there's the first few prime numbers, and that goes on, it turns out, forever. We're going to prove that in a later video. There's no particular pattern to the prime numbers. A lot of research goes into like trying to find a pattern or trying to predict what numbers are going to be prime or trying to find a formula that will spit out prime numbers. We don't have, like, there is no formula that tells you what this sequence of numbers is. The prime numbers and their distribution and the pattern within them are all kind of still a mystery to us. In fact, there may be no pattern, but like I said, that's still kind of an open area of research. So let's just before we move on, let's give a non-example. What is an example of something which is not a prime number? Well, 6 is not prime, since 2 divides 6 and 3 divides 6, right? There's two examples of things that divide 6 that are not 1 or 6, right? 6 is 2 times 3, so that's not prime. Now, whenever you have something which is not prime is called composite, because it is composed of other numbers, right? If it's composite, then it's composed of other prime numbers multiplied together. So that segues into the next thing I've got on here, which is a theorem. This is called the fundamental theorem of arithmetic. And it says that every integer n greater than 1 can be written uniquely as a product of primes. So what that means is that any integer n greater than 1 can be written as a bunch of prime numbers multiplied together. P1, P2, P1 times P2 times ... and then times Pk, for some k, however many primes you need. And it should be pointed out that within this product of prime numbers, you can have repeats. So like 2 is a prime number. You could have 2 times 2 times 2 times 2. That would be P1, P2, P3, P4. 2 times 2 times 2 times 2. It could be that all of those are the same number. Or you could have like 2 times 2 times 5 times 7 times 11, or whatever. And that would be another decomposition. This is called the prime decomposition of the number. and it's unique. And by unique, that means up to order. Like you can rearrange them, but if you write them in non-decreasing order from like smallest to largest with repeats, put together, if you write it that way, then that exact string of primes will be unique to that number. You're never going to have two different numbers with the same prime decomposition, because if they have got the same prime decomposition, then they're the same number. So that's why it's unique. Now, let's just give it a quick example. A couple examples here. 715, that's a number. It's composite. Its prime decomposition is 5 times 11 times 13. 175, its prime decomposition is 5 squared times 7. What about an actual prime number, like 19? Its prime decomposition is just 19. That's it. It's got only one number in its prime decomposition. What are some numbers that don't have a prime decomposition? Well, this says n greater than 1, right? So first of all, we're not really considering negative numbers because a negative number is just the opposite of a positive number. And so if you wanted to write the prime decomposition of that negative number, just stick a negative in front and then take the prime decomposition of the positive, of like the absolute value. So we don't really need to discuss negative numbers. It's just not important. But I think it is pointing out that 1 doesn't have a prime decomposition because 1 is not a prime number, it's just special. And 0 doesn't have a prime decomposition because it's also special. 1 and 0 are always special. So we don't really need to discuss the prime decomposition of those because they're, yeah. All right, so that's it. That's it for this video.